Okay. In circuit theory, the separation of charge creates an electric force. We can call this the voltage. It's also is a potential difference, right? Where we're unable to. It's like gravity, right? In gravity and physics, you have your potential energy, right? Okay, the further I go, I lose my potential energy. That way, the Earth can do work on me. Okay, that that same type of mentality you can apply to electricity, and that voltage is that potential for me to work. Okay, all right. Now, the actual moving of the charges, we term that the kind. Okay, it's think about it this way: if I'm a river and the water's electricity, okay, the difference in height physically would allow water to flow from point A to point B. Okay, let's say that height was a difference, potential difference of 5 volts. Over here I'm at 5 volts. Here I'm at 0. Okay, and the actual flow of the electrons going from point A to point B, that's the current, right? Even big the current of the water. Okay, so that the same way that we have current, and I got voltage, we got primitive understanding of this. Same way that we have done in physics, we're gonna apply it over here. Okay, so these concepts of voltage and current are useful from an engineering point of view because they can be expressed quantitatively, guys. Okay, you can express these with numbers, right? You can do calculations with them. Perform all the tasks that you got to do. Whatever positive and negative charges are separated, energy has been expended. All right, so it takes work, it takes energy for me to be able to remove things that are being attracted to each other. Okay, I got a positive, I got a negative. They just want to touch each other all the time. Right? I say, hey, you gotta pick it up. So I come in between and I pull them apart. Right? Spreading them apart, it takes work. Right? Have you ever tried to pull apart two things that are trying to be together? I didn't think so. Because it takes work. It really does. It really likes to waste their time. Right? Well, voltage is the energy per unit charge created by this separation. Okay? So the amount of energy that you end up using by 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 separating these things is the voltage. Okay, if I got electrons, they're negative. They're getting pulled towards the right. Okay, that energy per unit charge, voltage. Don't forget it. When I express this ratio in differential form as the you may have the definition of voltage, guys. Okay, gotta write these equations down. You can't be forgetting about them. They're very, very important. Right? I'm gonna write small. I like writing small. Voltage. V. V is from volts. Right? Now don't be scared about the W here over DQ. What does that mean? You see this notation in math. And some of this notation in math. Jane Rade something. It's typically a derivative. Okay, that's what we call it. Leibniz notation. All right, not Leibniz, whatever. Okay, so derivative is a rate of change. It's a small change in work over a small change in the charge. Okay, so voltage, change in work, which is energy in joules, divided by the change in charge, and the charge in coulombs. Okay, you can also say the derivative of the work with respect to the charge. It's not that hard. The electrical effects caused by the charges in motion depend on the rate of charge flow. The rate of charge flow is known as the electric current, which is expressed as we have this formula. Okay, I is current. conveyance voltage is current. Okay. Why? Don't ask me. Instead of dW over dQ, it's dQ over dt. Same logic from earlier. Wow, this doesn't want to draw a straight line. Wow, this is unbelievable. Okay, here we go. Finally. The very tiny relative change in charge. Tiny, relatively tiny change in time. The rate of change of charge over the rate of change of time. That's the derivative of the charge with respect to time. Okay? You guys got that one? Making sense? Right? Don't overthink this stuff. It's just kind change of charge with a change of time. You can't dt. Alright? It's a derivative. It's a very simple derivative. Alright? So the equations 1.1 and 1.2. These are written right here. 1.1 and 1.2. Right? We got voltage, we got current. So these equations, they define the magnitude of voltage and current respectively. Right? Definitions of voltage and current. They quantify them mathematically. Voltage, change of work on a change of charge. Current, change of charge over a change of time. Good? So, the bipolar nature of electric charge requires that we assign polarity references to these variables. Alright? See, someone's bipolar, you gotta have a polarity reference, right? Am I right? What does that mean? I'm bipolar. That means I can be either really happy or really sad. I can be really positive or really negative at any given moment. So, since I can be either both, I have to specify if I'm being bipolar, which kind I am, right? So if the charges are bipolar, that means I can either be really happy, really plus, or really sad, really minus. Okay? So, you better specify which one they are. Okay, charges, I'm gonna say many plus, many minus. Okay? You gotta specify. It can be one or it's either or. Okay? I mean, do so in section 9.5. Right? Inquiry is made up of discrete moving electrons. We do not yet consider them individually because of the enormous number of them. Like, I can just kind of think of it as one a big, unanimous blob. Rather, make it think of electrons as and their corresponding charge as one smooth and flowing entity. Okay? Thus, the kind, is treated as a continuous variable. One advantage of using circuit models is that we can model a component strictly in terms of the voltage and current at its terminals. This two physically different components can have the same relationship between the terminal voltage and terminal current. Okay? If this is the case, if they do, for purposes of circuit analysis, they are identical. And pink. If two physically different components have the same relationship between the terminal voltage and terminal current, they're in terms of circuit analysis, they're the same. Okay? Meaning, they do completely different things, but if they do the same thing with electricity, my China has the same object, like, they're pretty much identical. One component that may shape completely different. As long as I know the same thing electrically, they're the same. Okay? So once we know how a component behaves at its terminals, like it always is its behavior in a circuit. What does that mean? If I know that I had a voltage source, and on one side I'm gonna be positive, the other side I'm gonna be negative, and I know that there's gonna be a potential difference of 5 volts. I know everything that I need to know to incorporate this into my circuit diagrams, okay? Alright? I know exactly what it's going to do because I know its terminal behavior. Right? Once I plug it in, plus and minus, both sides. Those are the terminals, right? Plug it in. If I know what something does at the terminals, I know what it's going to do in the circuit. So, however, when developing component models, we are interested in the component's internal behavior, okay? So when you are making the component itself, you're interested in what it does on the inside, okay? It's helpful for putting the test together. Not really helpful in my opinion for this course. Right. Right. You might want to know, for example, whether charge conduction is taking place. Because if free electrons move into the crystallized structure of a metal, or whether it is because of electrons moving with the covalent bonds of semiconductor material, these concerns are beyond the realm of circuit theory. So in this book, you may use component models that have already been developed. What does that mean? Okay, so we're not going to deal with the physical phenomena involved with we're not due to the physical phenomena involved circuit. What actually makes the circuit run? We don't care about the way the electrons move, right?